Okay, so we have a few questions here from Chapter 8 that we're going to go over here. The first question was dealing with how much work to show on the divergence test. The example that the person wanted me to go over is actually one that you wouldn't use the divergence test on in the exam. I know in the homework it was wanting you to do this, but I believe this was 8.4, number 15. And it was asked to use the divergence test on this, which was k squared over 2 to the k. And when you have something like this, this is where you would use growth rates here. Remember, log grows much less than polynomials, much less than exponentials, which are much less than factorials, and there's even other ones that you can put into the list, but that's the general thing here. So if you want to say here the limit as k goes to infinity of k squared over 2 to the k power is, well, this is equal to 0 because 2 to the k grows much faster than k squared. And that's all you'd have to write down. The problem with this one is then the divergence test is inconclusive. And remember, on the exam, you'll always be able to apply a test to determine it. So let's go ahead and actually apply a different test here. The temptation might be to use the root test. But you don't want to use the root test. The reason you don't want to use the root test is this right here. The root test, you want the entire expression. You'd want this entire expression to some kind of k power, not just part of it. If only part of your expression is to the k power, you don't want to use the root test. You would want the entire thing here. Well, that also doesn't look like something I want to integrate, so this turns out that it's going to be a ratio test. So we'll look at r is equal to the limit as k goes to infinity, and it would be k plus 1 squared over 2 to the k plus 1 divided by k squared over 2 to the k, which is the limit as k goes to infinity of k plus 1 squared over 2 to the k times 2 times 2 to the k over k squared. My 2 to the k's would cancel, and so this would be equal to the limit as k goes to infinity of k plus 1 squared over 2k squared. Now, this is easy enough to multiply out, so I'll go ahead and do that. But you really don't have to multiply it out, because I know what the highest degree term in the numerator is going to be. The highest degree term is going to be k squared. But if I multiply it out, of course, you get k squared plus 2k plus 1 over 2k squared. And then you can evaluate this limit however we want. So I'm going to just do lead terms. Which of course is 1/2. And then so my r is equal to 1/2, which is less than 1, so the series converges. But let's actually look at an example here with the divergence test that might show up on the exam, as far as, and then what kind of work you would have to show for it. And this is going to seem trivial to some of you, and it's supposed to be. Now, what's going to be the deceptive part is this is going to be you'll see this problem, not this exact problem, but maybe something similar to this, and you'll have a whole blank page to do work. I'm giving you a whole blank page on all of the problems because some of the problems require a little bit more work than the others. But I'm not going to suddenly give you less space on one problem and more space on another, because if I give you less space, it might indicate, oh, well, that means there's not much work I have to do to solve this one. So I'm giving you a whole blank page for each one so that you have to really be able to discern what test to do. So if I look at this here and look at the limit as k goes to infinity of 3k squared minus 2k plus 1 over 4k squared plus 1. This is going to be the same thing as the limit as k goes to infinity of 3k squared over 4k squared, which is just 3/4. And so the limit as k goes to infinity of a sub k does not equal 0. So by divergence test, the series diverges. And you do need to write down what test you're using when you make a conclusion or a statement like this. But a whole page of work is what I'm not saying a whole page of work. There's going to be a whole blank page, and you're going to write barely anything for this problem. So people always second guess themselves because I've given you a whole blank page. There's got to be more work to show. No, there isn't, and I'm doing that on purpose because if I gave you a little bit of work space, you might say, oh, well, that's going to be an indication it's divergence theorem. So every problem has the same amount of space to do the work. You just have to figure out the correct technique to use. But that's all there is. So they're very divergence questions. If you can figure out which one's the divergence question, should be an easy 10 or 12 points. I don't remember how many points each question's worth, but it should be easy, quick to do. Okay, so I also had a question here on section 8.4, number 25. And this is sum from k equals 1 to infinity of k e to the negative 2k squared. Well, let's kind of go through the tests here again. I'm going to write them off to the side. Well, we can cross some of these off pretty quickly. We know it's not geometric. We know it's not telescoping. If you think about it for a second, this limit goes to 0, so it can't be divergence test. It's not root test because remember we want the whole thing to the k power, so it's definitely not root test. So I'm left integral ratio. Well, probably not the ratio, even though we used it on the previous one. We even said that, hey, ratio is going to often involve factorials, so probably the integral. Alright, so that means I need to set up an integral here. So I need to do the integral from 1 to infinity of x e to the minus 2x squared. Now remember, I said for the exam you're going to have to remember things like u substitution and integration by parts. And this is actually just a simple u substitution. I'm going to let u be not negative, just 2x squared. Then du is 4x dx, or 1/4 du is equal to x dx. And then if x is equal to 1, u is equal to 2. If x is going to infinity, u is still going to infinity. And then I'd have my integral that would be the integral from 1, from 2 to infinity of e to the negative u du. And then we would convert this to limit as b goes to infinity of the integral from 2 to b of e to the negative u du, which is the limit as b goes to infinity of negative e to the negative u, evaluated from 2 to b, limit as b goes to infinity of negative e to negative b minus negative e to the negative 2. But then if I think about this for a second, this term is going to go to 0 as you go to infinity. And so this is just equal to e to the negative 2. So the integral converges. So by integral test, the series converges. Okay? All right. Then I also had some questions here. I had a question dealing with the root test, seeing if we could do another example with the root test. So I'll go ahead and do one here, but then we'll get ahead and talk about how, if this was, for instance, on the exam, how would we know it's a root test problem? Now remember, root test, you have to be a tiny bit careful because sometimes you think you should apply a root test, but it's a geometric series. Remember, if there's just a number, inside here where I'm drawing the arrow to a k power, that is not a root test. That is a geometric series. But I don't have a number in here. I have an expression. So I have a whole expression here to the 2k power. So it's because I have something, yeah, it's to the 2k power, but I don't care that it's to the 2k power or the k power. It's all being raised to the k power here. So that means I'm going to want to use the root test. So I compute this row here, which is the limit as k goes to infinity of my expression, my a sub k, so that's to the 1 over k power. Actually, there's an error in here. This is supposed to be a plus. Sorry about that. All right, well then we continue on here. And what would we have here? We'd have limit as k goes to infinity, and now I don't need the square bracket anymore, because what do? We multiply those together, and so we'd have 3k plus 1 over 4 plus 2k squared. Now, even if you get the right conclusion, you have to make sure your work is correct. We have to figure out what this limit is. And some people might just say, like, oh, it's, you know, 4 or 3/2 or something like that. And, you know, you have to make sure that you get the right limit here. And so one of the things, again, this is relatively easy to multiply out. So let's just go ahead and multiply it out. So we have 9k squared plus 6k plus 1 over 16 plus, that would be 8, so 16k plus 4k squared. And then we can simply use, again, the lead terms. Now make sure you, when you do the lead terms aren't just necessarily what's first, it's what's the highest degree. But then we can clearly see this is 9/4. But wait a minute, rho is equal to 9/4, which is greater than 1. So by root test, the series diverges. Okay, so we got a couple more questions here. These were from 8.6. And again, these are kind of obvious for the exam. 8.6, remember, is dealing with alternating series. So we have negative 1 to the k power, natural log of k over k squared. And this is obviously alternating series because of the -1. So remember, there's always two things we're going to have to do here. Actually, this was number 14, by the way. Two things we're going to have to do is first determine if this thing converges. So we're going to look at the limit as k goes to infinity, -1 to the k, natural log of k over k squared, which is limit as k goes to infinity. Well, it's going to be plus or minus 1 times natural log of k over k squared. And we just have to think about growth rates. Polynomials grow much faster than logarithms, so that's equal to 0. And so we know the series converges. But now we need to determine what type of convergence we have on this series. So we need to look at the absolute value of this. Which of course would just be sum from k equals 2 to infinity natural log of k over k squared. Now this is probably the most difficult one to evaluate then, because looking at this, it's not a root test, it's not a ratio test, it's not geometric, it's not telescoping. Oh, we're running out of tests here. It's not divergence test. So that leaves the integral test. And so that's what we're going to have to do here. We're going to have to do an integral from 2 to infinity of the natural log of x over x squared, which we know is the limit as b goes to infinity, the integral from 2 to b of the natural log of x over x squared. Now this is where dx. This is where this one becomes a tiny bit challenging here. I'm going to rewrite this a second. Let's rewrite this one more time. Because I said you're only ever going to need to know two integration techniques for this exam: substitution method or the integration by parts. Well, this is not substitution, so this has to be integration by parts. But that's where you definitely want to remember your Lipit, log inverse polynomial exponential trig. So because it's clearly not u substitution, so it has to be integration by parts. So u needs to be natural log of x. dv needs to be x to the -2 dx. So du is, I'm going to write it as x to the -1 as opposed to 1 over x. And then v, integrating this, would be negative x to the -1. And so this would be equal to the limit as b goes to infinity of the, well, it's no longer an integral because it's u times v. U times v would be negative x to the -1 natural log of x evaluated from 2 to b minus v du. So we'd have negative x to the -2 dx from 2 to b. So I'm going to just clean this up a little bit here before I continue on. Alright, so doing that, as I said, the integration, you have to remember that Lipit thing there, because if you remember it, u becomes a natural log, and you can see I'm going to be able to do this integral here, the x to the -2. So I've got negative x to the -1 natural log of x evaluated from 2 to b, and then I'm going to have minus x to the -1 evaluated from 2 to b as well. Now I'm going to go ahead and rewrite this as the limit as b goes to infinity of the natural log of x over x minus 1 over x from 2 to b. So this would be limit as b goes to infinity of the natural log of b over b minus 1 over b minus natural log of 2 over 2 minus 1/2. But let's think about this for a second. These go to 0. And this is just, I'm not even going to bother computing it. I'd want you to compute it on the exam, but this is just some number. So what do we get here? Well, we get that the integral converges. So the series converges. But now let's remember what was the original thing. So what we have here ultimately is that the original series that we were looking at converges absolutely. All right, one more question here that I had, and it was on number 46 from the same section. Whoops. Okay, so clearly another alternating series, and so we have to look at what the limit as k goes to infinity of -1 to the k plus 1 times e to the k over k plus 1 factorial. Now this is really where you just need to remember growth rates, and this is how you would answer this question on an exam. But the growth rates, remember, are logs grow much slower than polynomials, which grow much slower than exponentials, which grow much slower than factorials. So what does that mean? That means this, I'll put it in quotes, reaches, because we can never actually reach it, reaches infinity first. It doesn't actually get to infinity, but it gets bigger first. So that means the limit as k goes to infinity of -1 to the k plus 1 e to the x over k plus 1 factorial equals 0 by growth rates. So you need to give some kind of explanation. If you just say it's equal to 0, I'm going to say, well, that's, how do you know that? You know, why is that obvious? It's obvious by growth rates because of this little line here. So you should write down this red line here, and then you can say, oh, well, that goes to 0 because of growth rates. All right, but then we have to determine if it's absolute or conditional convergence. So we are going to, of course, look at the absolute value of this. Sorry, just spaced out there for a second. I'm not doing limits yet. We're looking at the series. Absolute value of -1 to the k plus 1 e to the k over k plus 1 factorial, which of course just becomes the series k equals 1 to infinity of e to the k over k plus 1 factorial. And this one should scream at you at what test to apply now. This should scream at you as the ratio test. So to apply the ratio test, of course, we go r is equal to the limit as k goes to infinity of e to the k plus 1. Now it's already k plus 1, so it'd be k plus 1 factorial divided by e to the k over k plus 1 factorial. So I'm going to write this out in a couple steps here. So I'd have e to the k plus 1 over k plus 2 factorial times k plus 1 factorial over e to the k. And then we'll split apart, just like we've been doing in all of these. So you'd have k plus 2 times k plus 1 factorial. And we can quickly see these e to the k's go down, these k plus 1 factorials go away, and so you're left with r being the limit as k goes to infinity of e to the first power over k plus 2, which is equal to 0. So we know that the series converges now, and just remember what we're actually determining here is then that this series from k equals 1 to infinity of negative 1 to the k plus 1 e to the k over k plus 1, we can now claim that this converges absolutely. Alright, well, good luck on your exam, and I will see you the following week.